Look, some of the students, around 20 to 22 students wrote me about today's class, to take today's class. Only those are present, or others are also present? Others are not willing to come today. What is the matter?
Like it was informed in the department group that there's a class today.
Acha, Sanmukh Sai Vardhan, let
Yes.
me. Okay, you are there. Ayush Iran. Ayush is there. Snehobandhu.
Yes, ma'am, I'm here.
Pooja Sharma. Pooja Sharma is there. Abhishek Kumar.
Yes, ma'am.
Ayush Surana.
Yes, ma'am.
Devesh Govind. Are you there, Devesh Govind? Yes, Yen. Yes, Jen. Suraj Kishore.
Yes, ma'am.
Aditya Jha. Aditya Jha. Abhishek Purohit. Yashvi Jain. Vivek Surekha. Somil Bharilya. Sajad Ansari. Shashank Gautam.
Present, ma'am.
Vidabomma Sai Venkat.
Present, ma'am.
Okay. So out of these 21, 22 people who wrote me, some 5, 6 are not present today. And I see others are present, like Samira, Chinmay, Rushi Girish, and who else? Only 30 students. Jyotirinda, Katra Kushal, Mushkan, Nidhi, Tejas.
Yes, ma'am.
Yes, it's fine. Polami, Pratik, Rakesh, Raunak Agarwal, Tanay, Sahil, what happened? Sanmukh Sai Vardhan, you only raised this na today's class?
Yes, ma'am. It was after the discussion only.
Then not discussion, you wanted, and your friends supported you. So I came today. No problem, I can take the class. But the thing is, I don't get interest if only 30 students are present na, out of this 95. You call your friends.
Yes, ma'am.
Who supported you?
Like I have informed in the department group.
Only informing does not help. Call them.
Yes, ma'am. Sure.
So let us start the class. I do not want to waste time. Already 15 minutes are almost over. Mole balance of a differential reactor. Look, Differential reactor is mm, a continuous reactor where catalysts are set in a form of catalyst bed at the middle of a tube. It is a tube. It is a tubular reactor. At the middle of the tube, catalyst bed is situated, and okay, I just did. This is the first slide. So look at this slide. Here, this is the differential reactor. At the middle of the reactor, we have a thin bed of catalyst. Catalyst particles are poured in the form of a thin bed, and the other sides are filled with inert filling like glass beads or ceramic beads, etc. So, differential reactor is used to determine the rate of the reaction as a function of concentration or partial pressure of the reactant, usually what we do. But it is in the flowing condition, it is a flow reactor. It is a tube containing very small amount of catalyst in the form of a thin wafer or disc. Thin wafer or disc. Now, what is a differential reactor? What are the characteristics of a differential reactor? These are major 3 points. One is the conversion of the reactant in the catalyst bed is extremely small. So the conversion we consider is very small. So the inlet and outlet concentrations are nearly the same. Because catalyst bed is very thin, and the conversion against this catalyst bed, inlet and outlet, is considered as very thin. So whatever the concentrations of the inlet, concentration of the reactants at the inlet is almost equal to the concentration of the reactants at the outlet. The reactor is assumed to be gradientless. That means concentration gradient is negligible. Difference in concentration is negligible. Reactor is assumed to be gradientless, and the rate of the reaction is uniform throughout the reactor. So, uniform throughout the reactor means uniform throughout the catalyst bed. Catalyst bed is a thin plate type. As the conversion is very low, so the heat change during the reaction is also negligible. Reaction happens in a very low conversion, so all the reactions are associated with some heat change, but as here we consider the conversion is very low and the difference in the concentrations of the inlet reactant to the outlet reactant is very little. So heat change associated with the reaction is also very low, which we can neglect. Hence, the reactor is assumed to be isothermal. These are the assumptions for a differential reactor. Now, conditions of a differential reactor. What are the 2 conditions? One is reactants should not bypass the catalyst bed. All the reactants molecules should pass the catalyst bed. It should not bypass. That is, channeling must not occur. Channeling means when the reactant fluids just bypass the catalyst bed somehow through the void space at the boundary of the catalyst bed without just touching the catalyst beads. That is the channeling. Channeling should not occur in a differential reactor. All the reactant molecules should pass through the catalyst bed, and catalyst life should be long in order to maintain the same rate of the reaction for a sufficiently long time. You know, if the catalyst life is short, the catalyst get deactivated soon, then obviously the conversion will be changing. So as here also the here we have thought that conversion is very low, but there is some conversion obviously, otherwise we cannot calculate the rate of the reaction. So if the catalyst remains in the same activity for a long period of time, the rate of the reaction will also be same for a long period of time. These are the conditions. Now, this is the, obviously we have to do the mole balance for designing a reactor. Mole balance of a differential reactor. The volumetric flow rate throughout the catalyst bed is monitored. Here we have taken only, look at this picture, we have taken only the catalyst bed, this part in the reactor. Although it is showing two-dimensional, but think it is a three-dimensional small thin circular cylinder, and these are the catalyst particles which are just poured inside the tubular reactor in the form of a thin cylinder. The volumetric flow rate through the catalyst bed is monitored. Entering and exiting concentrations are also monitored in this reactor. Here, let us consider W, small w is the weight of the catalyst in the reactor. Fa0 and FAF are the inlet and outlet reactant molar flow rates respectively. This phase it is Fa0, that phase it is FAF. Reactant say A. Ra in the unit of moles per gram of catalyst per second. Ra is the rate of the reaction. V0, small v0 and small VF are the volumetric flow rates of reactants initially and finally respectively. F is denoted by the molar flow rates and V is denoted by the volumetric flow rate. Same inlet volumetric flow rate of the reactant A is V0, and after at the other side of the catalyst bed it is VF. That means after the reaction. Ca0 and Ca is equal to the initial and final concentration of the reactant. Cp is equal to product concentration. So here Ca0 is the concentration of A at the beginning before the reaction, and only Ca is the concentration of A after the reaction, and whatever product is formed, very small amount, because conversion is very low, we have taken it as a Cp, product concentration. Steady state mole balance on reactant A, we have to wait for the steady state, and then we can do the mole balance. So at steady state, what is the mole balance? Flow rate in minus flow rate out plus rate of generation is equal to rate of accumulation. And as we consider there is no accumulation within the catalyst bed or within the reactor, so it can be written as 0. So flow rate in is the molar flow rate Fa0, flow rate out FAF, and rate of generation is rate of the reaction per mass of catalyst, which we have shown. Throughout the mass of the catalyst into mass of the catalyst will be the rate of generation of any product is equal to 0. So Fa0 minus FAF plus Ra. Ra's unit was per gram of catalyst, so we have to multiply it with the mass of catalyst. Ra into W is equal to 0. Minus Ra is equal to Fa0 minus FAF by W. This is the mole balance equation for differential reactor. Now this equation, this original equation, we can write in different forms. In terms of concentration and volumetric flow rate, we can write, look, this molar flow rate is equal to the concentration into volumetric flow rate. If you see the units, it is Fa is the mole per second, Ca0 is the mole per cc, and V0 is equal to cc per second. So ultimately it is giving us mole per second. So Ca0 into V0, instead of Fa0 we can write, instead of FAF we write Ca Vf by W. In terms of product conversion or flow rate of products, we can write minus Ra is equal to Fa0, sorry, Fa0 XA by W. XA is the percentage conversion or fractional conversion of A. Fractional conversion of A into the mole flow rate, that means mole per second, will give you the molar flow rate of product by W. This much Fa0 into Xa, this much A is converted because we are multiplying the flow rate of A by the by the fractional conversion, and that conversion is actually towards the product. So it is the molar flow rate of product. X is the conversion of reactant to product, Fp molar flow rate of product. When stoichiometric coefficients of A and P are equal, say 1 mole A is giving 1 mole of P, like that, then Fa0 into Xa is equal to Fp. We have taken same molar conversion. If it is different, then obviously some coefficient will come. The constant volumetric flow minus Ra is equal to Vz. Constant volumetric flow minus Ra is equal to V0. Say if it is a constant volumetric flow of the reactant, then V0 and Vf are equal. So we can take out the V0 out of the bracket, and it can be written as V0 into Ca0 minus Ca by W. And Ca0 minus Ca is the product formed. Initial concentration of A minus final concentration of A is giving you the product concentration. So we can write V0 Cp by W. Here the rate can be determined by measuring the product concentration. For very little catalyst weight and large volumetric flow of A, very little catalyst weight means the conversion is very low, and if the volumetric flow of A is very high, then the conversion is very low. So the concentration difference inlet and outlet of A is also very low. So Ca0 minus Ca, this difference in concentration is very small. Therefore, what happens, if they are almost equal, we can say that it is rate of the reaction is dependent on the average of the concentrations of A at the inlet and outlet. So minus Ra is equal to function of CAB. CAB is the average concentration at the inlet and outlet. CAB is equal to Ca0 plus Ca by 2. Therefore, rate is a function of average reactant concentration within the catalyst bed. Now, as we have considered that Ca0 minus Ca is very small, then we can write Ca0 is almost equal to Ca because their difference is very small. So here, if you put Ca0 plus Ca0 by 2, because Ca is almost equal to Ca0, so then ultimately what is coming? This average of concentration is Ca0. However, very little conversion is assumed for differential reactor. CAB is almost equal to Ca0. Therefore, minus R is a function of Ca0. Now, for just a moment. Class আছে, class করছি। Hello. Now let us for construction of rate equation for a reaction done in a differential reactor, we can take the reaction data in various ways, and depending on the type of data, our rate will be different. So here we have taken a same say reaction C to B plus P. The data can be arranged in tabular form as below. How we can write the data? here this is run number. In the table you see 5 runs are taken. PC is the partial pressure of the reactant C, it is cumin, and P is the partial pressure of propylene, B is the partial pressure of benzene. And corresponding rates are minus RA, this minus RA1, RA minus RA2, minus RA3, this way. Look at the first run. In the first run, we have taken 0.5, PC is 0.5, that means either 0.5 atmosphere or whatever, and PP is 1 and PB is 1. For the second run also, say PC is 1 and PP is 1, PB is 1. Third run, PC is 2, PP 1, PB 1. Fourth run, PC 1, PP 0, PB 0. Fifth run, PC 2, PP 0, PB 0. And their corresponding rates are calculated. Here, if you look at the table, you see that when the reaction is starting at the beginning, for the first three runs, some products are also mixed with the reactant stream. With the PC, some PP and PB are mixed for the first 3 runs, and the corresponding rates are calculated. But for the 4th and 5th runs, the PC is not mixed with the product concentration products. So first 3 runs are what are the first 3 runs? The rate of the reaction which we have calculated are called the product inhibited data. Here product is having some inhibition effect on the reaction. Look, if you look at this reaction, C is equal to B plus P. If you start the reaction with C, but along with C some B and P are mixed, then obviously that concentration of B and P, the products, will inhibit the rate, will have some influence on the rate of the reaction. Even if you think about as the Laws-Atelier principle also, this happens. But if only C is there, no B and P are mixed with C, then the rate of the reaction which you will get are those are called pure feed data, are something different than the other 3 data. So these are the different types of data we can use for the for determination of the rate of the, or these are the situations. These are the different situations occur when we carry on a reaction in a reactor. Any reactor, it is not only for the differential reactor, any batch reactor or continuous reactor, other continuous reactor, this may happen. All the design equations for ideal catalytic or fluid solid reactions can be obtained from their homogeneous reactors analogues. Actually, for the solid catalytic reaction, you understand that we cannot construct a rate of the reaction expression very confidently, because many things are happening in different steps of a solid catalytic reaction. We cannot write it with confidence what we can write for the homogeneous reactions. So what is done for simplicity's sake, at the beginning, for getting the rate of the reaction, we consider the homogeneous reactor analogues, similar type of reaction rate expression for heterogeneous reactions also. For all the design calculations, it is not actual, but for getting some simplified data, we can use sometimes. All the design equations for ideal catalytic or fluid solid reactions can be obtained from their homogeneous reactor counterpart, by substituting reactor volume V for homogeneous with the catalyst weight W for heterogeneous. you understand that for the homogeneous reactions, reactor volume is important because that is contained in a reactor. And the reaction happens throughout the reaction volume if there is no catalyst present, solid catalyst present. But whenever there is a catalytic reaction, the reaction occurs only on the catalyst surface, either internal or external, but not throughout the volume. So instead of reactor volume for the homogeneous reaction, what we do, we replace that with the catalyst weight W. The reactor volume for heterogeneous reactor is calculated by V is equal to W by rho B. Rho B is the bulk density of the catalyst. Bulk density is actually the density of the catalyst taken as a whole. That means taken its solid portion of the catalyst, also the pore, that means void portion of the catalyst. It is bulk density is that. Actually, whenever you make a catalyst bed in a tubular reactor, then what happens? The catalyst, as I have shown you here, look, these catalyst particles, same size particles almost, they are packed inside the catalyst, inside the tubular reactor. Look, these catalyst particles are having pores in them. These small dots are there inside every catalyst particles. So those dots may be considered as the internal pores. And also there is some external void spaces also. And those small void spaces are there between the 2-3 particles, a triangular small void space. So as a whole, this whole stack is taken as the one catalyst section whose density has been determined by the weight of the catalyst and also the volume of the catalyst bed. Volume of the catalyst bed is considered as the catalyst particle, which volume it is occupying, all the catalyst particles, and also the void spaces by the in between the catalyst and outside the catalyst also. This is bulk density. For an ideal batch reactor, how we can replace the homogeneous part by the heterogeneous, here it is shown. For an ideal batch reactor, the differential form of design equation for a heterogeneous reaction is minus RA is equal to 1 by W dNA dt is equal to 1 by W. W is the catalyst weight. Instead of, you have read in your homogeneous part of reaction engineering, it is actually rate of the reaction is written as minus RA is equal to 1 by V dNA dt. So instead of V, we are writing W. Same equation, dNA we can write dNA0 into XA. XA is the fractional conversion. Na0 is the initial mole, and so Na0 initial mole is constant, so it is coming out of this differential form. So Na0 by W dXA by dt minus RAW is equal to Na0 dXA dt. dXA dt is the rate of the reaction in terms of conversion, fractional conversion. Any question in this part? Any question? No. Now we can see that how temperature affects the rate law. Usually, you know, the gaseous phase reactions occur at high temperature, and specific reaction rate constant K follows Arrhenius temperature dependence and increases exponentially with temperature. As you increase the temperature of the reaction, rate constant will increase, rate will increase, rate constant will increase. Usually, it is seen that at every 10-degree rise in temperature, reaction rate doubles. So now for the solid catalytic reactions, you know, always the reaction occurs through the adsorption step. First adsorption occurs, and after that reaction occurs on the solid catalytic reaction. So you know, the adsorption of all species on the surface is exothermic. Adsorption is an exothermic process. So higher the temperature, smaller is the adsorption equilibrium constant, because adsorption equilibrium constants become smaller, Ka by K of minus A. This is the adsorption equilibrium constant. Ka is the adsorption constant, rate constant, forward rate constant, and K of minus A is the reverse rate constant. So if the temperature increases, then what will happen? More desorption will occur. So K of minus A will be more. So Ka by K of minus A, this value will decrease. So capital Ka adsorption equilibrium constant will also decrease at higher temperature. Now, if adsorption equilibrium constant decreases, therefore the denominator of the catalytic rate law approaches 1. If we see the rate law for a reaction A to B, irreversible rate equation, which I have shown you yesterday, A to B, how we write the single site rate equation, minus RA is equal to Kpa by 1 plus Kapa plus Kbpb. Now, at high temperature, the adsorption equilibrium constant of A and B, Ka and Kb, are very small. Then what will happen? The denominator will approach towards 1, because 1 plus this part is very small. So it will be nearing to 1. So what is left? Minus RA is equal to Kpa. This we can write. At high temperature, that is lower surface coverage. Lower surface coverage means desorption is more. 1 is very, very high compared to Kpa plus Kbpb. Therefore, minus RA is equal to small k into Pa. Small k is the adsorption rate constant, forward rate constant. For a reversible reaction, obviously here the reversible reaction terms will come minus something. So it is Kpa plus minus Pb by Kp. Kp you can remember that big constant which is reduced to small kp, this 1 Kp. So this is the expression of reversible reaction occurring at high temperature. We can never really prove a mechanism by comparing the derived rate law with the experimental data. From the experimental data, you can, for the heterogeneous type of reaction, you cannot, I said, you cannot confidently claim that this is the rate of the reaction. But usually what happens, what is the mechanism in which pathway the reaction is occurring, whether it is single site or dual site, or it is Langmuir-Hinshelwood type of kinetics following, or Illet-Redoux type. We cannot confidently say. Only we can do continuously, we can put our experimental data in different derived rate equations, which we assume this may be the rate equation, and find out whether it is matching with our expectation or not. But we can do the spectroscopic or tracer analysis. Tracer experiments are needed to prove the mechanism. That means spectroscopically we can follow the reaction, how it is occurring. Sometimes it is not possible, and tracer experiments are with maybe some isotopes. We can see how the isotopes are progressing, how it is changing its character. This way we can predict a rate equation or mechanism, rather. First mechanism and then rate equation comes. Until we cannot prove the mechanism, we cannot proceed for the rate equation, because rate equation depends on the mechanism. To reduce the catalyst weight, the temperature of the reacting mixture should be increased. Look, catalyst is a costly substance, so it is better if we can use a small amount of catalyst. And if you increase the catalyst weight, then obviously the reaction rate will increase, more conversion will occur, because more catalyst active sites are obtained with higher catalyst weight. But we try to make a optimum catalyst weight by optimizing the reaction temperature. It is usually at a higher temperature site, but the problem of higher temperature is that some side reactions also occur at higher temperature, which is undesirable. Now, evaluation of rate law parameters. What are called rate law parameters? Let us see, assuming a reaction A dot S plus T, T is in the gas phase, say T is not adsorbed, giving us the product B, which is adsorbed on surface side S. Now, we can write this equation, rate equation, surface reaction as the rate limiting step, minus RA is equal to Kpa Pt by 1 plus capital Ka plus capital Kb. Small k is the surface reaction forward rate constant, Pa is the partial pressure of A, Pt is the partial pressure of T, and as T is not adsorbed, so we don't write T term in the denominator, any T term. A and B are adsorbed, so we have to write 1 plus Kpa plus Kbpb. What are the rate law parameters? Rate law parameters are rate constant, Ka adsorption equilibrium constant of A, adsorption equilibrium constant of B are to be determined. These are rate law parameters. These are to be determined by analyzing the experimental data in the best possible way. This is called parameter estimation. The way to find out rate law parameters is called the parameter estimation. How we can do? We have to do it mathematically, different ways. Graphical method we can do the least square analysis or non-linear regression, etc., by which we can solve the equation. This one is linearize this equation, and we get this, and we can use 3 sets of experimental data to find out 3 unknowns: K, small k, capital Ka, and capital Kb. So if we have different data, Pa, Pt, Pb, and rate of the reaction, three different data, we can construct 3 equations, and we can solve the 3 equations to get the 3 unknowns. So this way we can determine the rate law parameters. Now, what is called catalyst deactivation? Catalyst deactivation means, I said that already previously, that whenever we use a fresh catalyst in a reaction, obviously the rate of the reaction will be high, the conversion is very good, and as the time goes, the activity of the catalyst decreases because the active sites gets deactivated by the because of exposing at high temperature for a long period of time, and continuous adsorption and desorption. So they slowly decreases its activity, and ultimately one time will come when we don't get the economical conversion. Whatever conversion will give us the cost effective production, we don't get. At that time we have to change the catalyst. So what are the reasons for catalyst deactivation? One reason is sintering or aging. What is that? It is the loss of catalytic activity due to loss of active surface area. For a long time, if the catalyst surface is exposed at high temperature, then what happens? Some parts of the catalyst gets melted, and because of the melting, that part, the crystals or surface sites are destroyed. Now, it is the loss of catalytic activity due to the loss of active surface area resulting from prolonged exposure to high gas phase temperature. The active surface area may be lost either by crystal agglomeration, either crystals or molecules get agglomerated, they form a non-reactive part on the surface. The crystals which the form of crystals or shapes of crystals which are responsible to take the molecules of the reactants for the adsorption, that shape may be destroyed, or they get melted and the sites are destroyed. And growth of metals deposited on the support. If you use impure stream, then the impurity will sit on the support, on the catalyst surface, or by narrowing or closure of the pores inside the catalyst pellet. Because of the high temperature exposure, the pores may get closed. Their mouths may be closed, become very narrow because of the melting or change in the crystal structure. A change in surface structure may also result. So these are the consequence of exposure to the high temperature for a long time. This is one. Aging means because of the time, a long time exposure, aging occurs, it does not retain its activity. Another reason is fouling or coking. This mechanism of decay is common to reactions involving hydrocarbons. Hydrocarbons are consisting of hydrogen and carbon molecules. Most of the many compounds are actually hydrocarbons. So if you use hydrocarbon in a hydrocarbons, maybe methanol, ethanol, all these are hydrocarbons, and many others, many acids, acetic acid, and many things are hydrocarbons. So whenever you use these compounds for a reaction, hydrocarbon compounds, then what will happen? For a long period of time, these molecules will get disintegrated at high temperature and form coke particles, pure carbon, or a highly carbonaceous material which contains high amount of carbon in it, which is actually called coke, and those are deposited on the surface of the catalyst. As they are deposited permanently on the surface of the catalyst, the active sites are no longer exposed to the reactant molecules, so activity is lost. Poisoning. Poisoning is another reason. This deactivation occurs when poisoning molecules are irreversibly chemisorbed on active sites. Poisoning molecules means they may be different molecules which are catalyst poisons. They destroy the activity. Say arsenic is sit on the you are using a stream which contains impurity as arsenic. Those impurities are different types like heavy metals, vanadium, nickel. They may get adsorbed on the catalyst active sites. Chemisorbed. Chemisorbed means a very tight bonding between the impurity and the catalyst site, and they chemisorb irreversibly. That means they don't get dissolved. So thereby the number of active sites are reducing for the not available for the main reaction to occur. These are the reasons for deactivation. Now we are coming to another chapter. Till now we were discussing with the 3 steps only: adsorption, surface reaction and desorption. We did not consider the diffusional steps. Diffusional steps are quite obvious for a reaction, solid catalytic reaction, solid catalytic fluid phase reaction. Diffusion we cannot avoid. So let us first let us discuss with these diffusions, and these diffusions or mass transfer are having some resistance on the resistance effect on the reaction. How they are, this chapter we will discuss. Here the mass transfer effect on the overall reaction rate will be discussed. The reaction rate will include both chemical reaction and resistance to mass transfer. So rate of the reaction will include not only chemical reaction part, but also the resistance to mass transfer is having a great effect on the reaction rate. You know the what is the diffusion? Diffusion is of 2 types. One is external diffusion, which is the reactant molecules coming from the bulk phase to the catalyst surface. This is one diffusion, and while traveling this path, the reactant molecules face some resistance of their own molecules. So this is the diffusional resistance, which is external diffusional resistance. 2 types of diffusional resistance are focused. During diffusion of reactants or products, products are also getting diffused from the surface of the catalyst to the bulk phase, the last stage. There also it is facing resistance of the molecules which are there in the bulk phase. During the diffusion of reactants or products between the bulk and external surface of the catalyst. And internal resistance is that during the diffusion of reactants or products from the external pellet surface to the interior of the pore. So look, the concentration difference is driving force obviously for the diffusion. Let's just think about this. A molecule of say reactant is waiting at the pore mouth to go inside the pore surface to get adsorbed on the pore active sites. While traveling from the pore mouth towards the internal surface of the pore, it is facing the resistance of the as the pores are very thin. So obviously the thin pores are posing resistance on the reactant molecules to come inside. And inside molecules are also there, other molecules. So this is internal resistance to mass transfer. We'll today discuss some fundamentals of diffusion which you might have known. What is diffusion? Movement of species from high concentration to low concentration relative to bulk movement. what is the net movement of the species from high concentration to low concentration relative to bulk movement. Say in the gaseous phase, always the molecules are moving, which is called the Brownian motion, you know. But except this Brownian motion, what is the net movement or net travel path of the molecule from high concentration to low concentration? That is due to the diffusion because of this concentration gradient. The molar flux of a species A due to a concentration gradient against a fixed coordinate is defined as, look at this, this is the 3 coordinate system x, y, z, and if a molecule is traveling this way, WA, this is the molar flux of A, we can divide it as I WAX, J WAY, K WAZ, I, J, K are the unit vectors. So this way we can split the molar flux into 3 coordinates. WA is moles per area time, flux, moles per area time is the flux. Now WA is equal to JA plus BA. What is JA? JA is the molar flux due to the diffusion relative to the bulk movement, and BA is the bulk flow, which is also bulk flux, bulk flow. So where JA is the diffusional flux relative to the bulk flow and BA is a bulk flow or bulk motion. Together will give you the total molar flux of a molecule. Now say UA is the total molar velocity of A. U dashed is the average molar velocity of A due to bulk motion. Say U dashed is only for bulk motion and UA is the total molar velocity. Then what happens? UA minus U dashed is the velocity due to diffusion. UA is the total, U dashed is for bulk. So UA minus U dashed is the velocity due to diffusion. So we can write it this way: UA is the total molar velocity, is the U dashed molar velocity due to bulk motion plus UA minus U dashed, that is velocity due to diffusion. Now you can multiply both sides by the concentration of A. CA UA is equal to CA U dash plus CA UA minus U dash. We can write it this way. Now CA UA is WA, total molar flux. And we can do one thing, we can take out CA out of these two quantities and we can write UACA plus UBCB by C. C is the this quantity, UACA plus UBCB by C is the molar average velocity due to bulk motion. B is also species in the gaseous phase. As it is constructing A and B total gas flow, which is constructed by A and B together. So C is the total concentration of A and B. And this is giving you the average molar velocity due to bulk motion. But in the bulk, there is B, but although we are looking at A, but we cannot neglect B. B and A constructing the total gas phase, and A is flowing due to the diffusion. A is having the concentration difference. So this way we can write WA is equal to CA UA. It is the total molar flux of A. Now WA is equal to this one, we can write CA by C. CA concentration of A and C is the total concentration of A and B together into UACA plus UBCB plus JA. JA is the JA is this one. JA is this one. Ca UA minus U dash, which is due to the diffusion. So due to the diffusion, flux is Ja. This notation we have used before. So it is ultimately coming Ca by C UA Ca plus UB Cb plus Ja. Now you see Ca by C is the mole fraction of A in the gaseous phase. It is written as Ya. Ya is the mole fraction of A, and UaCa is Wa and UbCb is Wb plus Ja. So this way also we can express the total molar flux in terms of the mole fraction of A and diffusional flux of A. Now, if we consider the fixed first law of diffusion, we can write diffusional flux as Ja is equal to minus Dab C nabla Ya. This is the this nabla Ya is the mole fraction in 3 coordinates. So, and Dab is the diffusivity of A in B, and minus sign is due to the concentration is decreasing from high concentration to low concentration. That is the reason we are putting minus sign in this fixed first law of diffusion. C is the concentration, total concentration in moles per decimeter cube, and Dab diffusivity of A in B, and nabla Ya we can write as I del Ya del X plus J del Ya del Y plus K del Ya del Z. So all 3 coordinates we can divide this Ya so that we can cover the 3-dimensional view. Putting Ja in equation 1, so this value, if we write in this equation, Wa is equal to Ya, Wa plus Wb plus Ja, we can write is Ya into Wa plus Wb plus minus Dab C nabla Ya. You may not consider all the 3 coordinates. You can use only one coordinate. That way also you can write the fixed first law, and you can write here also. But I have considered all the 3 coordinates. So you see similar way we can write previously what was there. Wa is equal to Ca U dashed, it is for the bulk motion, and plus minus Dab C nabla Ya, this is for the diffusional flux. Now the diffusion may be of 3 different types. One is equimolar counter diffusion. If 1 mole of A goes to a given direction, 1 mole of B goes to the opposite direction. If this is the situation, then obviously Wa is equal to minus Wb. Therefore, Wa is equal to, we can write in that same equation, plus Ja plus Ya into Wa minus plus Wb. So this quantity cancels out. Wa is equal to minus Wb. It is coming as only Ja, that is minus Dab C nabla Ya. This is the expression. Wa is equal to Ja is equal to this. This is the expression for EMCD, equimolar counter diffusion condition. Another condition is dilute concentration. Here the bulk motion is considered to be small because the concentration is very low. If the concentration is very low, number of molecules are less, so bulk motion is considered to be small. So only the diffusional motion is considered. So Ya into Wa plus Wb, that is the quantity for the bulk motion term, can be neglected. Here again Wa is equal to Ja. This equation can be applied to porous catalyst system. Porous catalyst, solid catalyst system, where the pore radii is very small. If pore radius is small, those are capillary pores, then what happens, there is a high resistance to enter inside the pore for the reactant molecules. So inside the pores, the concentration is very small. If it is so, then we can consider the case of the dilute concentration inside the pore. Then WA is equal to JA. This type of diffusion under this condition is called Knudsen diffusion. Knudsen diffusion is that Knudsen diffusion occurs in the dilute concentration when Knudsen diffusion, this diffusion occurs when mean free path of the reactant gas molecules is greater than the diameter of the pore. Diameter of the pore is so thin that when due to Brownian motion, the gas molecules are always going from one place to another. They are just moving from one place to another. So that pathway of Brownian motion, which is called mean free path, if the mean free path is greater, it is longer than the diameter of the pore, what happens? The molecules will impinge or collide on the surface of the pore more often than with each other. Always the molecules are colliding with each other, gas molecules. This is due to the Brownian motion. If the molecular Brownian motion pathway, which is called the mean free path, is longer than the pore diameter, then what will happen? The molecules will collide in much more frequency with the wall of the pore compared to the collision between two molecules between them. So here the reacting molecules collide more often with the pore wall than with each other, and molecules of different species do not affect each other. This is called the Knudsen diffusion. The flux of A for Knudsen diffusion, when bulk flow is neglected, we neglect the bulk flow because of the dilute concentration. Then we can write WA is equal to JA is equal to minus dk C nabla YA, where dk is called the Knudsen diffusivity. Here the diffusivity is changed because of the dilute concentration and solid catalytic, porous catalytic reaction. Where the thin pores are there, we have to use the Knudsen diffusivity. Diffusion through a stagnant gas, when A is a solute gas in the mixture of A and B is stagnant. If B is stagnant, then molar flux of B is 0. Then WA is equal to JA plus YA into WA plus WB. Is WB is 0, it is coming JA plus YA WA. This is for the condition when diffusion through a stagnant gas occurs. When it is a mixture of gases A and B is stagnant, A is diffusing, then we can write this expression. Is there any question?
What could be the example of this in that B is stagnant and A is diffusing?
There is no such example. I cannot give you a concrete example. It happens sometimes. There is no such a fixed example. It is the condition which may occur. So it is an assumption at present, you can say.
Yes, ma'am.
Any other question? Students, you practice, I'm telling you, for the examination and for other thing, you have to practice the this wait, let me take out of what you can practice is like I showed you the when the rate limiting step is adsorption, how we can deduce the rate equation. This I have shown in my lecture, but I did not show when surface reaction is rate controlling, how the rate law can be deduced. This I did not show. And also the desorption. I did not show those two. You practice those two. Like if I say this question, deduce the rate law for the reaction C to B plus P, reversible reaction, when surface reaction is rate controlling. The reaction is a gas phase solid catalytic reaction. You can you practice this, and also when desorption is rate controlling, how you can deduce the rate equation. Okay, I'll upload the again two notes today. Previously also I have uploaded other notes. You read those notes, study properly, and consult. If you wish, you consult the this book. What is that book? Book is not Levensville, another one. Wait. I have given you two books, names of three books. No. The second one, chapter 10. Chapter 10 of second one, you do. I just can't remember the name. I should not. Wait. Yes, Fogler. H. Scott Fogler. I told you on that day the Scott Fogler expired on 21st of August. He is a very renowned professor of chemical reaction engineering. Fogler's book, you collect Fogler's book, and Fogler's book is an easy book. You can read it. Chapter 10, Catalysis and Catalytic Reactions. I do not know whether in your edition that will be a chapter 10 or not. The name of the chapter is Catalysis and Catalytic Reactors. You can consult with that chapter. And today I have started the next chapter, which is the diffusional effects on heterogeneous reaction. Okay. So if you do not have any question, I am leaving then.
So, ma'am, the test is going to be next Friday.
Next Friday. Okay.
Okay, ma'am. And
ma'am, can you upload your slides?
Yes, I'll do. I already uploaded four PDFs.
Ma'am, you have uploaded the fuel laboratory ka slides. So
Is it?
yes, ma'am.
Sorry, let me see. Let me check it.
Yes. Thank you, ma'am.